Alright, elephant in the room. I know this is going to make everyone a little nervous, but we've got to talk about it. Yeah, I'm talking about formal charge. So sometimes, even when you follow the rules for Lewis structures, you'll wind up with different structures that can work out. And so then how do you know which is the right one? Could be that there's multiple elements in the compound that have the same electronegativity, which means that you can't really figure out who's supposed to go in the middle. So in order to figure it out, we have to use formal charge. And the way you recognize which structure is the right one is once you've calculated the formal charge, the Lewis structure will have the formal charge that are closest or equal to 0. If there are negative formal charges, they should reside on the more electronegative element in the structure. We'll see what this means once we practice it. So here's our first example, nitrogen trichloride. The problem is both nitrogen and chlorine has a formal charge value of 3.0. And so is it going to be nitrogen in the middle or is it going to be chloride in the middle? Well, in order to figure that out, we have to use formal charge. When we calculate formal charge, we have to do it with every element that is in the molecule. So you don't calculate a single formal charge for the entire compound. Instead, you calculate it for every element. And so the formal charge is equal to the number of valence electrons assigned to the neutral atom. So we're looking at a particular atom, a particular element inside that compound. How many valence electrons does it come with? So you look on the periodic table for that one. Like if it's phosphorus, it would be 5. If it's carbon, it's 4. Oxygen, 6. And the number of electrons assigned to the atom in the structure. So once you've drawn that Lewis structure, how many electrons does it have on it? And this is a little bit trickier, so we can see down here, this is just that part brought down. What this number is equal to is the number of lone electrons around the atom plus the number of bonding electrons divided by 2. So we do count the lone pairs, and we count the number of bonds divided by 2. So remember, each one of those covalent bonds, like if it's H to Cl, that covalent bond right there would only be 1 electron from the chlorine and 1 from hydrogen. That's the divide by 2. Alright, so keep that equation nearby while we're going through these so you can do the numbers yourself. On this table there should be a line right there to split those. We're going to calculate the valence electrons and the electrons assigned, and then from that we'll get the formal charge. So the number of valence electrons for nitrogen, we would go to the periodic table. It's in group number 5, so that means nitrogen has 5 valence electrons. And chlorine, each of those is going to have 7. So what we're doing here is we're finding the formal charge for all of the atoms that are in here. So you see there's 4 different atoms. We're going to find the formal charge for each of those. Alright, electrons assigned. So nitrogen has 1 bond, so that would be plus 1. For the second part, and then the number of lone pairs, it has 2, 4, 6, so it'd be 6 plus 1. That means it has 7 electrons assigned. This chlorine right here, so we'll call that one this guy, it has 2 for a lone pair, and then for bonded electrons it has 2, 4, 6 electrons. Divide that by 2, that's 3, so 1, 2, 3 for the 3 bonds, and that means it would have 5. And then these chlorines on the outside, you can see that they're the same. They would have 1 bonded pair and then 2, 4, 6, so they would be 7, just like the nitrogen. And then the formal charge is just a matter of subtracting those 2 values. So 5 minus 7 would be negative 2. 7 minus 5 would be positive 2. And then 0, 0. So the goal of a formal charge is to be as close to 0 as possible, if not exactly 0. So looking at these numbers right there, negative 2, positive 2, 0, and 0, this structure is not likely to occur. It's got too many non-zero values in it, and they're on different ends too, negative 2, positive 2. So this structure right here, more than likely, without even looking at the other one, isn't likely to occur. Okay, let's do the same thing with this other structure. Why don't you go ahead and pause the video and see if you can do this yourself. So all of the chlorines are the same, 7 and 7. Nitrogen was 5. That means, in the end, when we subtract those 2, we would have 0, 0, 0, 0. What that means then is that this structure is very likely to occur because we have the most 0 numbers inside of our formal charge. So of the two, if we were just compare the formal charges, this would be the structure that we would pick. Now, okay, when I first showed you guys these structures at the beginning, a lot of you probably picked out this one as the correct answer anyway. If you remember last year, we said that nature tends towards symmetry. And so, yeah, of course the nitrogen's going to be in the middle and the chloride's on the outside. However, a couple reasons why you have to be able to know how to do this. Number one, it's not always that simple. Number two, a lot of times in the AP test, they're going to ask you to calculate the formal charge for the sake of calculating the formal charge. So you need to know how to do it. Even if you know what the Lewis structure is supposed to be like, you have to prove it with formal charge calculations. Here's an example where the whole nature tending towards symmetry thing doesn't quite work. Sulfur and carbon both have electronegativities of 2.5. Nitrogen is higher, so we know it's not on the middle, but carbon versus sulfur in the middle? Who can tell? We can! Give this a shot again, see if you can do it, resume the video and check your answers. So here's the one with sulfur in the middle. Let's do the formal charges for it. So for carbon, we would have 4 and 6, and that's going to mean it has -2. Sulfur, we would have 6 and 4, so it's going to have a value of 2. And nitrogen is going to have 5 and 6, which means -1. So this structure, not likely to occur. We don't have a single 0 on there, -2, +2, -1. Let's look at the formal charge for the other structure, though, anyway. Try this one out, then resume the video and see how your answer matches up with mine. Okay, so when we do the calculations for this one, carbon 4, 4, that means 0, 6, 6, that means 0, nitrogen 5, 6, that means -1. Hey, when we look at this one, we can see that it's not all zeros across the board like it was for the other guy. We do have a -1, but there is more zeros in this structure than there was in the other one. But that's actually okay, because if we sum up the formal charges, 0 plus 0 plus -1, the total formal charge is -1, which matches with the charge of the molecule. So that's okay. Okay, if our formal charge total matches up with the charge of our molecule, that's actually a good sign. It means that it makes sense. Also, the negative charge resides on the most electronegative species. That's also an important thing. We talked about that in one of the earlier slides, that if the negative charge falls on the least or most electronegative element, that means it's probably going to be okay. Alright, do me a solid and draw yourself the Lewis structure for sulfate, SO4 2-. Make sure you follow all of the rules, and then we're going to go ahead and check to make sure our answer is correct using formal charges. So step number 1, we're going to put the least electronegative element in the middle, that's sulfur. We've got the oxygen surrounding it, and we've already got our brackets around, giving us a -2. Step number 3, we complete the octets for all terminal atoms, so we've put the 2 valence electrons on either side of the oxygens, giving us a total of 6, meaning that we have 8 electrons around each oxygen. And then finally we're going to sum up, and we started with 32 valence electrons. We've done 4 sets of 8, so that means we're at 0 right now. That means that we can attach any leftovers. There's 0 leftovers, so we're good. At this point, we would normally say, check and done. But just because we're all a bunch of nerds at home with no friends, let's go ahead and find the formal charge on the atoms in here. So it's going to wind up being the same thing for all of the oxygens, because all the oxygens are identical. We would have 6 on the neutral atom. We would have 7 bonded, and so that means it would equal -1. And so all of those oxygens on here are going to be -1. Uh-oh, that's not a good sign. We have 4 -1s on this guy, and the charge is -2. Not a lot of zeros here, and it doesn't match up with the charge of the molecule. Let's check out the sulfur, too. The sulfur, it has 6 normally, and it's got 4 bonded, so 6 minus 4, that is +2. Oh gosh, so if we sum this up, nah, that's not going to work, you guys. So even though this looks correct, formal charge tells us this structure is not likely to occur. So if we increase the bonds between sulfur and oxygen, what we can end up doing is changing the formal charge. So by decreasing the number of lone pairs and increasing the number of shared pairs on the oxygens, what's going to happen now is these oxygens that we have double bonded still started with 6, but now they have 6 that are attached to them, giving us a total of 0. So all of those double bonded electrons, 6 minus 6 equals 0. And the sulfur, now that it has double bonds, is also going to be 6 minus 6, giving us 0. Hey, this is great. We have 3 zeros on there, and the overall 0 plus -1 plus 0 plus 0 plus -1 gives us a total charge of -2, which does match up with our total charge on the ion. So using multiple bonds, we were able to eliminate some of the formal charge and give us a better structure because now it matches up with how it should. So sulfate SO4, it looked okay before according to the rules, but formal charge tells us there's a better way to draw sulfate, and here you see it with the expanded octet around sulfur. So that's it with formal charge. More than likely, when we see Lewis structure problems, they're going to specifically tell you to figure out what this structure is based upon formal charge. So it's not like you need to do this process for every single Lewis structure we draw. Just be ready to if you're not sure about the way it looks or if you're asked to.